Okay, hey, welcome back. Let me see if my microphone's on. Microphone's on. Okay, sorry if that was loud. Anyway, yeah, so welcome. We are going to talk about first-order linear differential equations and methods to solve them. So last time we talked about the separable differential equations, and so this was a method of exploiting the chain rule. And through doing the chain rule, basically we were able to actually separate the two different variables into two integrals that we need to take, and that led to a lot of implicit solutions to differential equations and some explicit solutions depending on the situation. So now we're going to move on to that was one first order differential equation, and now we're moving on to a second first order differential equation, but this one is where they are linear. Now the big trick here is we're actually going to be exploiting the product rule this time, and so this is sort of a theme of all of calculus if you haven't noticed. We basically learned the chain rule, we learned the product rule, we learned a couple of the really basic things, and then they're all being co-opted into other sort of techniques, and basically that's all we can really do with calculus. So we know, for instance, the chain rule was used for U substitution back in Calc 2 and in or Calc 1 depending on your class. And then when we went to talk about integration by parts, that was basically just inverting the going backwards from the product rule, and so that invented a whole new technique. And so now we're at yet another point where we are going to be using the product rule as a technique, and what this involves is something called an integrating factor. So in general, the form of these equations can be written as dy dx plus p of x times y is equal to some q of x. And the idea is that we want to rig a product rule that we can just sort of invert. And the way you do that is you take p of x and you take its integral, and then you put that into an exponential function. And that sort of artificially makes a function that when you take the derivative of it, it's going to end up giving you that function back times p of x. So then if we take that integrating factor and we multiply through, what you get on the left-hand side is you get the integrating factor times d by dx plus the integrating factor times p of x times y. And we made it so that p of x times the integrating factor is actually the derivative of the integrating factor. So that entire left-hand side then can be reduced to just being d by dx of the integrating factor times y. And then you can use the fundamental theorem of calculus and take the integral and get rid of the derivative. Now what that leaves you with is just the term on the right-hand side that you need to integrate. And that's going to use your standard integration techniques such as U substitution or integration by parts or whatever else comes up. Trig sub is possible. But at the end of the day, you actually have a solution to the differential equation. Even if you have to just leave it in integral form, you still have solved for y. And so here we're going to end up with a whole bunch of explicit solutions to differential equations, and where we're going to basically take that integrating factor times y is equal to the integral of whatever q of x was times the integrating factor plus some constant, and then you can divide by the integrating factor, and today you've solved y. And so so that makes these a really nice sort of differential equation. And we're going to end up using them when we go and talk about section 3.2 out of the book. And this one is going to be a whole bunch of sort of inflow, outflow sort of problems and mixing problems. And it turns out that the resolution of all of these problems boils down to linear differential equations of the first order. So you're going to use this technique a lot. And so yeah, anything else I wanted to talk about? No, I think that's good for this lecture. All right. Sorry to rush it through. I only get these small windows to actually record. So anyway, let's go ahead and jump into it. Okay, so let's go ahead and get started. So today what we're going to be talking about are basically differential equations that are linear. I don't like that color. Let's change it to blue. So we're talking about linear equations of the first order. And in particular, this corresponds to section 2.3 out of the Nagel, Saff, and Snyder's book. This is Fundamentals of Differential Equations, 9th edition. Hey guys, so if we go back to the definition of what we called a linear differential equation, I think this was out of section 1.1. They gave us this. They told us that a linear differential equation is an equation that takes this form. So a1 of x times dy dx plus a naught of x times y is equal to, say, b of x. Right? And so basically we have a linear equation if dy dx and y appear on their own, and the only thing that's really attached to them is some function of x, right? And so we couldn't have, say, y squared. That wouldn't count as that would be a nonlinear differential equation. And so so that's okay. So if we take a look at, say, the first example, what we have is we have x squared sine of x minus cosine of x times y is equal to, say, sine of x dy by dx, right? And so they're telling us that this is linear. It doesn't look like it's in this form yet, but it's easy enough to move it around. If I move, say, this guy over to the left and, say, this guy over to the right, or actually even more simply, I just move this around over here, then what do I get? I get sine of x times dy dx plus cosine of x times y is equal to x squared sine of x. So in this case, sine of x plays a1 and cosine of x plays a naught. And here, this is b. Now, the book doesn't actually even go into giving you the solution to this differential equation, and it's actually a really nice build-up to what we're going to be talking about in a second. So what we can see is if I were to call this function, say, mu, or maybe not to make it slightly less confusing for what's coming, let me just call this, say, I don't know, something else. Call it, say, z of x. You'll notice that this is actually z prime of x. Now this is the basic idea that comes into doing the product, linear equations, is that we actually want to be able to rig up something where we're going to have a function here and its derivative here. And then if you look at d by dx of z times y, well, this is going to be z times y prime plus z prime times y, right? And so you're going to be looking for this, and you're going to try to go backwards. And so that's exactly what we have here. We have the derivative of y times z, and then we have y times the derivative of z. And so that tells us that we can change this equation to just being d by dx of sine of x, that was our z, times y. And now this is equal to x squared sine of x. Okay, so now what I can do is I can use the fundamental theorem of calculus, and what this is going to give me is on the left-hand side, it gives me this. Sine of x times y is equal to the integral of x squared sine of x by dx plus c. So now we need to just figure this out. This, again, is not terribly hard. It is an integration by parts, so it takes a little bit of time, but don't get intimidated by the amount of work you're going to see. It really is just integration by parts. I'm going to have to apply it twice. So let's go ahead, just so we get some room. We're going to take this equation here, and we're going to copy it over to the next page. So let's see, copy, boop, and next page. There you go. Okay, so now let's take a look. So I want to go ahead and compute this integral. So let me go ahead and do that. So I have the integral of x squared sine of x dx. Now I know no matter what if I were to choose sine of x as u, I would get cosine, and then if you do integration by parts, you get sine again, and if this was part of my dv, then we'd be going x cubed, x to the fourth, x to the fifth. It would be going up in x's. So what we want to do is we want to do the opposite of that, right? So we're going to choose this guy to be my u, and this is going to give me x squared,
And then if I take du, that gives me 2x dx. And so we've gone down in power. And then that tells me that basically if I do this again and just use x or 2x as my u next time, then I'll be able to pull out, reduce it by yet another power. So that leaves dv is going to be sine of x times dx. And that tells me then that v is equal to minus cosine of x. All right, so now we know that the integration by parts gives me uv minus the integral of v du. So we're going to have x squared times negative cosine of x minus the integral of v du. Since v has a minus sign in it, I'm going to pull it out there. That leaves me a cosine of x and then times 2x dx. And this is the du part. Okay, so now I come up to a new equation. Here we're going to choose du is equal to, say, 2x. We're going to choose u to be 2x, and then that leaves du is equal to 2 dx. And we're going to have dv is equal to cosine of x dx, and that leaves v is equal to sine of x. All right, so now let's go ahead and see what we get. So I going to still have this minus x squared cosine of x plus, let's see, so we get, again, the new u is 2x, and the new v is sine of x, minus the integral of v du, so sine of x, and it was just 2 out of du, 2 dx. Okay, so this is the integral of this guy, and so finally we get sine of x times y is equal to minus x squared cosine of x plus 2x sine of x minus 2 cosine of x, flip sign there, and then plus c. So I basically forgot to integrate that there, but that's easy enough. That's just negative cosine, right? And so that's what flip sign, right? And yeah, that's quite a mouthful. And I think everything's correct. It's the right number of terms, I think. We have an x squared term, then we'll reduce it to an x term, then reduce it to a constant, and so yeah, that fits. Finally, if we want to solve for y, we go ahead and divide by sine of x. So we get y is equal to minus x squared cosine of x over sine of x plus 2x sine divided by sine, they just cancel, and then plus 2 cosine of x over sine of x plus c. If you wanted, you can write this as a cotangent of x, and that could be written as cotangent of x. On the exam, I wouldn't really care about that part, not unless it's a really significant reduction. Because if you want to compute cotangent of x, you're just going to change it back to cosine over sine. And I guess, yeah, so that's the first example. Oh, and I forgot, c should also get that, sine of x. We're dividing everything here, and so, yeah, and that's going to be kind of a feature that we're going to see, is you're going to have c times some sort of function. Okay, so let's go back and take a look at what happened. So we got kind of lost in the woods there, but we started here, and we selected this as being our first example. It's in the book, but they don't actually work it out. And we recognized that we had some sort of product rule that we're able to sort of undo. And so that gave us this. And after we undid the product rule, we recognized we had z times y prime plus z prime y, and we know that gives us this. And so after that, it's just a matter of using a fundamental theorem of calculus, and you can kill that guy on the left, the d by dx, by integrating both sides. But then that leaves you with the integral you have to do on the right-hand side, and so that's where all the work came in here. So the work came into integrating the right-hand side of that, and so that was just integration by parts done twice, and so ultimately gave us this. And then finally what you do is just divide by this guy here, and that isolates y. Okay, so the real game here and the whole technique that we're going to be developing is we want to come up with a way where we don't just get lucky and get a product rule, but we'd actually like to have some method that'll always give it to us when we want it. All right, and this works for specifically linear differential equations of the first order. All right, so let's go ahead and take a look and see what we can do. So in general, what we're going to be given is we're going to be given a differential equation, and we're going to usually isolate dy by dx. And so it's going to give us dy by dx plus p of x y is equal to, say, some q of x. And this is going to lead us to what is called an integrating factor. So this integrating factor is going to be something we call mu of x, which is equal to e to the integral of p of x dx. And when you do have that as an integrating factor, what you're going to notice is that we have mu of x prime is equal to just p of x times e to the integral of p of x dx. So basically, e sticks around, but then by chain rule, it kicks out the derivative of the integral of p of x. And so that's why that pops out there. So then what we notice is that this is just p of x times mu of x. And so if I was to multiply mu of x by both sides, what we see here is that this guy is just mu prime. And so so then what we can do is we can undo the product rule. And what we get is this. We get d by dx of mu times y is equal to q of x. And we should have had mu over here too, because we multiply both sides by that. So times mu of x. So then I would like to isolate y. So I'm going to integrate both sides using a fundamental theorem of calculus. And so that's going to give me a mu of x times y is equal to, say, the integral of q of x times mu of x dx. And hopefully this is something we integrate. Sometimes we're kind of left with not being able to. And then plus a constant. And then finally, our general solution then is going to be 1 over mu of x times the integral of q of x times mu of x dx plus c over mu of x, right? And so this is the general procedure. And this is just becomes routine after you do it enough. So let's go ahead and take a look at a couple of examples. So so let's see, example what they call 1 in the book. So this will actually be our second example. So they want us to find the general solution of 1 over x dy by dx minus 2y over x squared is equal to x cosine of x, and they want us to hold for x bigger than 0. Okay, so what I'm going to do is first is I need to figure out what p of x is. So I first need to isolate dy by dx. So multiplying both sides by x, I get dy by dx minus 2 over x is times y is equal to x squared cosine of x. All right, now let's go ahead and take a look at what our integrating factor would have to be. So first we need to identify p of x. P of x is not 2 over x. P of x is minus 2 over x. So this whole thing is p of x. This is 2. So let's go ahead and figure out what mu should be. Mu is e to the integral of p of x, so it's going to be minus 2 over x dx. And so this is going to give me e to the minus 2 times the natural log of the absolute value of x. Remember, x is bigger than 0, so I can just write x anyway. So then this is going to be e to the natural log of x to the negative 2. And so ultimately this gives me x to the negative 2, and we had negative 2 there because we can take the coefficient out in front of the logarithm, make it an exponent, right? And so then now I can just use the inverse feature. Now it's just natural log and the exponential. You can't use the inverse until you have everything inside the natural log. So then what I get is x to the negative 2. So mu is x to the negative 2. Now I want to multiply both sides by x to the negative 2. So when I do that, I get 1 over x squared dy by dx minus 2 over x cubed times y is equal to, well, x squared divided by x squared is just 1. So then I'm left with cosine of x. which is nice because I was really kind of dreading doing integration by parts again. Okay, so now let's take a look. So this was my mu, 1 over x squared. And so what should end up here, it should be the derivative of mu. And indeed, mu is 1 over x squared. And so if I take the derivative of that, we're going to take x to the negative 2. We're going to have a negative 2 pop out. And then we're going to decrease the exponent by 1. So it's going to be negative 2 times x to the negative 3. And indeed, that is exactly what this is. So now I can go ahead and see that we have d by dx of 1 over x squared times y is equal to cosine of x. Integrate both sides, and so using the fundamental theorem of calculus, this is 1 over x squared times y is equal to the integral of cosine of x plus c dx. And ultimately, I have y over x squared is equal to sine of x plus c. Now I multiply both sides by x squared, and I get y is equal to x squared sine of x plus c times x squared. And that is the general solution to this differential equation. So again, what we did is we first isolated dy by dx here by multiplying by x. And so then that left me with what we called p of x. P of x goes into our integrating factor, and so it goes right here. And then I just integrate, and that gave me a negative 2 natural log of the absolute value of x here. We knew that x was bigger than 0 because we were told so, and so then I can remove the absolute values, and then I move this guy into the exponent. Once I did that, I could invert the natural log using the exponential, and I get x to the negative 2. I multiplied x to the negative 2 on both sides, and then I'm left with mu of x, which was x to the negative 2, and its derivative here. I can recognize then that this whole line here is a product rule, and so I undid the product rule like this. So it is just a derivative of this product. And fundamental theorem of calculus, I get to cancel the derivative. And what happened on the right-hand side is that we end up having an x squared, ended up getting canceled away, it left us with a cosine. Cosine's easy to integrate, and it gave us sine, and then we just multiplied back over by x squared, and we won, and that was the game. So that's how you do these sort of problems. Okay, so the next one is actually a preview of section 3.2 that's coming up in the book. And let's see. So this one, they have some sort of radioactive decay problem. So this is example 1. So they have some sort of radioactive isotopes. So they have Ra1 and Ra2. They don't tell us what they are. But they say that belong to the same radioactive series. That's cool sounding. So basically one decays into the other. So that's what that means. So yeah, that's what they say. That is Ra1 decays into Ra2. Which then decays into stable atoms. All right, so assume that the rate at which Ra1 decays into Ra2 is 50 times e to the minus 10 t kilograms per second. Okay, and we say because the rate of decay of Ra2 is proportional to the mass y of t of Ra2 present we have the rate of change in RA2 is this. And so they say d, remember y is how much RA2 we have, so we say dy by dt is equal to in rate minus our out rate. So, and in this case, our in rate is 50 times e to the minus 10t. That's how much we're decaying from RA1. And the out rate is some proportion of whatever volume we have. It looks identical to a lot of the problems we're going to be talking about in section 3.2, which I think is coming next, maybe? We'll see. Okay. So, yeah, okay. So let's see what the problem is. Okay, and so they say where k is a constant of proportionality. Okay. So if k is equal to 2 per second, and initially y of t, or y of 0, is equal to 40 kilograms, find y of t, the mass of RA2, for t bigger than 0. Okay. All right, so that's a lot of stuff to say, but it really boils down to a pretty simple differential equation. So we have dy by dt is equal to, let's see, what was it, 50 times e to the minus 10t minus 2 times y of t. If you want to double check that all these constants work out, k was per second, and so we have kilograms per second, and so going into a derivative that matches that side. And let's see, and the in rate actually comes with kilograms per second as well. So all of our units match up, so I can, at this point, just ignore them from here on. Okay, so first thing we want to do is we want to write into that form where we have dy by dt plus 2y of t is equal to 50 times e to the minus 10t, right? So now we have our p of x here, and so we have our p of t in this case. So p of t is equal to 2. Again, we're looking for our integrating factor, so mu of t is going to be e to the integral of p of t dt, and so that's equal to e to the 2t, because p of t is just 2. Okay, now we multiply both sides, and so we get e to the 2t dy by dt plus 2e to the 2t times y is equal to 50 times e to the minus 10t. Okay, now if I look closely, if this was mu, well, that is definitely the derivative of mu, and that we get that by chain rule. So we recognize product rule, and so we have e to the 2t times dy by dt is equal to 50. Oops, I forgot to multiply it on the other side. So I multiplied by e to the 2t here, but I forgot to multiply here. And so what that would ultimately get me is be minus 8t. Okay, so we have e to the minus 8t here. Now I integrate both sides. Oops, and again, I made another mistake. That should have just been y, right? So this is a product rule, and it just becomes this. All right, so there we go. Sorry about that. All right, now I integrate both sides, and I use a fundamental theorem of calculus. And so I get e to the 2t times y is equal to 50 times e to the minus 8t, and we're dividing by minus 8. So then I get plus c, and then I get this. I get y of t is equal to 50 over minus 8 times e to the minus 8t plus c divided by e to the 2t. Right, and, sorry. It's tired. Okay, so we get 50 divided by minus 8, we're dividing both sides by e to the 2t, right? So this needs to decrease by 2. And so it's going to be e to the minus 10t plus c times e to the minus 2t. There we go. Okay, so mostly done. So we have an equation so this is going to be our general solution. But what we're missing here is we are missing our initial condition. So we need to add that back in so we can figure out what C is. Because this is a very particular collection of atoms, and we want to say, all right, for this particular collection of atoms, what's going to happen? We don't care about the general, we want the very specific. So I remember that y0 should be equal to 40, and so then that's going to be equal to minus 50 over 8 times 1 plus, because we're put 0 in here, that gives me 1, and then plus C, and again 0 in here gives us 1 out of that term. And so what I get then is I get 40 plus, let's reduce this, 25 over 4 is equal to C. And so then I get 185 over 4, I think, is equal to C. So that tells me that y of t is equal to minus, say, 25 over 4 times e to the minus 10t, and we get plus 185 over 4 times e to the minus 2t. And that is our answer. Okay. Cool. Let's see. All right, so now let's take a look at another example. And this one is what they're saying is should be a computational example. And is this last? It's the last example of the section, so we'll get through this pretty quick. I might throw up an example of showing how we can actually resolve this, but let's see. So here we have the initial value problem. So I say for the initial value problem, and they give us y prime plus y is equal to the square root of 1 plus cosine squared of x for y of 1 is equal to 4. They want us to find y of 2. Okay, so first of all, we need to solve this differential equation. A nice thing is that they actually already wrote this out in the standard form, so we can go ahead and pick out the p of x, which is going to be 1. So then that tells us that mu of x is going to be e to the integral of 1 dx, which is equal to e to the x. All right, that's nice enough. If I multiply both sides by e to the x, I get e to the x times y prime plus e to the x times y is equal to e to the x times the square root of 1 plus cosine squared of x. Okay, now I recognize the left-hand side is just d by dx of e to the x times y, and the right-hand side is e to the x square root of 1 plus cosine squared of x. There's nothing nice to do there. I integrate both sides, and so I'm going to get e to the x times y by the fundamental theorem of calculus. And on the other hand, I'm going to write, it's going to be integral from, say, 0, or say, rather, so the integral from 1 to, say, x, I'm going to put t's on the inside, so I'm going to have, because you shouldn't have your bounds having the same variable, so 1 plus cosine squared of t dt, and then plus some c, and we can figure out what that c has to be in a second. So we have that, we have y of t is equal to 1 over e to the x times the integral from 1 to x of e to the t square root of 1 plus cosine squared of t dt plus c over e to the x. All right, now we're told that y sub 1 is equal to 4, so if I put in y of 1, I can figure out what c has to be. That's going to be 1 over e times the integral from 1 to 1 of stuff plus c over e, and the integral from, with the bounds matching, is going to have a width of 0. And so that is equal to 0. So this is just going to be c over e, and since this should be equal to 4, that tells us that C is equal to 4 times E. Okay, so what does that leave us? We now have this much. Y of x, that should have been x. I started saying t and I got carried away. Y of x is equal to 1 over e to the x times the integral from 1 to x of e to the t square root of 1 plus cosine squared of t dt plus 4. Okay. Now they asked us what is y sub 2, and that's going to be 1 over e squared times the integral from 1 to 2 of e to t integral of 1 plus cosine squared of t dt plus 4. And now we're left with having to figure out what this is. Okay, so this is going to have to use a computer of some kind, or if you're really industrious, hand calculations. But this we're going to use something like, say, the right-hand rule. Could be the midpoint rule, Simpson's rule, etc. But basically, we have some sort of integral that we're trying to compute, and so we're going to chop this up in a whole bunch of little pieces, and we're going to get an estimate on what that should be. And and so that'll give us some rough estimate of whatever y of 2 should be. I'm not going to ask you to do that. What I would ask you to do on the exam is I would like you to get to this point. Don't give me an actual numerical answer. I would ask you to give me sort of written out how that would be. And so here we ended up, so let's go ahead and talk about this. So recapping, we were given this differential equation that we wanted to solve, and we couldn't actually solve this in a nice closed form. At the very least, we could pick out p of x, and we could come up with mu of x. Sort of the biggest part of this whole linear differential equations. I multiplied both sides, and I got this. And on the left-hand side, I just undid a product rule, just like we did before. On the right-hand side, however, we ended up with a differential equation we couldn't quite solve. And so when we integrated both sides, we just had to leave it as an integral. You can still do some solving around it. For instance, I was still able to divide by e to the x, and it got me here. And we can solve for c just by noting that since this integral was starting at 1, because that's where our initial value started, if I plugged in 1 on this side, the whole integral disappears. And so once we realized that that was 0, all we're left with is 4 is equal to c over e. And that told me that c was equal to 4e. So then plugging that back in, we just get 4 over here. And then at the end of the day, we wanted what y of 2 was. And so we plug in 2 and we got that. So not too bad. So the big takeaways from this lecture, though, is identifying what p of x is and developing this integrating factor. And that is the most important thing. This extra bit where you have to worry about this sort of integral, it can come up here and there, and I think I have a problem in the homework talking about that. But that's not nearly as important as making sure you get down this integrating factor. So make sure you get some practice at that and undoing the product rule from here to here. If you have questions about that, please do ask on Canvas if you're part of my class. If you're not part of my class, you can ask on YouTube if you like. But as far as my class goes, I'd rather they just keep their questions on Canvas. Also, we are a little concerned about privacy issues, and so I'd rather my students not be posting on public forum. But in any case, that's the lecture, and I hope you found it helpful, and we'll cut back to my outro.
Okay, so I hope I was able to get the idea across to you. Really, these are very straightforward problems. You just take find that p of x, turn it into an integrating factor, and then what you do after that is you multiply it through and you get a product rule, and then the rest just comes down to whether or not you can integrate the right-hand side. Should be, hopefully I made it clear in the video. If you need more help, just go ahead and ask me. and I'll try and make a subsequent like homework help video or something in the future. I guess I got a notification. I think it's probably my screen time report. That's so annoying. I try to edit these so I don't have to. I try to silence everything so I don't have to edit these afterwards. But you know what? I might just leave that in because I'm tired and I have to keep up with the schedule. Anyways, yeah, thank you for watching, and good luck with your learning.